So here we define splitting field. The splitting field for a polynomial f over a field is the smallest field extension, the smallest e that you could find, such that the polynomial f factors into a product of degree 1 terms where these alpha, alpha 1 up through alpha n are elements in the field extension e. So the splitting field is the smallest field that you can split your polynomial up into linear terms. So let's do some examples. The splitting field for the polynomial x squared plus 1, and let's say I'm over the rationals, is q adjoin the complex number I. That's because I could take x squared plus 1 and write it as a product of terms x minus I times x plus I, and plus and minus I are elements in this field extension. The splitting field is not the complex numbers because the complex numbers are not the smallest field that contain this property. Now, if I said x squared plus 1 was in the field of polynomials over the reals, if I removed this q and put an r there, then the splitting field for this polynomial would be the complex. Okay, let's do another example. The splitting field for, let's try, how about x to the third plus 1. Let's again try the rationals. Well, to find this, I'm going to try factoring this into linear terms. I see that this polynomial does indeed have a root that's rational because I can see that negative 1 is a root of this polynomial. So I have that x cubed plus 1 is x plus 1 times x squared minus x plus 1. This here, this is an irreducible over the rationals. You could see that there's no root. Rational root theorem does it right away. So I'm going to let alpha be equal to 1/2 plus the square root of 3 over 2i. The roots of this polynomial are alpha and the other complex number, 1/2 minus square root of 3 over 2i. You can get this using the quadratic equation. So the splitting field is q adjoined alpha. If you adjoin alpha to the rationals, you can find that this element is also in the same field. So this is my splitting field. All right, here is a theorem. Take a polynomial, f of x, with coefficients in your field. A splitting field exists. Okay, so we're going to prove this by induction on the degree of f. So here is a proof by induction on the degree of f. If the degree of f is 1, then it's already a product of linear terms, and I'm done. So the base case, I think, is taken care of almost trivially. So the fundamental theorem of field theory, so the fundamental theorem of field theory says that there is a field E that contains a root, let's say alpha 1 of F. This was the field that we got by finding an irreducible polynomial that divides F and then looking at the factor ring of polynomials modded out by the ideal generated by that irreducible polynomial. So that's the field E. And thus I can divide and I can write f of x as x minus alpha 1 times some other p of x where alpha 1 is in E and p of x is a polynomial possibly with coefficients in E, let's say. Okay, well, the degree of P is less than that of F, so we proceed by induction on this P of x to get f of x is x minus alpha 1, and then P of x I can write as alpha times x minus some other alpha 2, and so on, times x minus alpha to the n for some field extension E2. So that means I can extend the field F to find this kind of factorization. So the splitting field it's the smallest possible field that contains alpha 1 through alpha n as roots. And so therefore, the splitting field is the field adjoined alpha 1 up through alpha n. It's the smallest possible field that contains these roots. Okay. So I'd like to finish this video with another quick observation or theorem. The field F is algebraically closed if and only if the splitting field for any polynomial f of x with coefficients in your field is f. So is f itself. So the splitting field is actually just the field f. You didn't need to enlarge your field to write your polynomial f as linear terms if f is algebraically closed. Okay, so let's write down the proof of this. So the reason why this is true is, well, I've got an if and only if statement. So if f is algebraically closed, then every polynomial, so if f is algebraically closed, every polynomial f has a root in the field. In particular, if f is algebraically closed, this field adjoin the roots of this polynomial is just f itself. So the splitting field is this field, but with the hypothesis that it's algebraically closed, that's just f itself. So that's that direction of the proof. For the opposite direction, so let's say that if the polynomial f of x in this ring of polynomials has splitting field f, then that means your polynomial can be factored as linear terms, but everything here is in your field. So I have a root. So alpha 1 is a root of your polynomial in your field. That's the definition of algebraically closed. If you take an arbitrary polynomial, it will have a root in your field. Okay, wonderful. I'll see you for the next video.